So you see, building up a charge and storing a charge so you can do experiments with it to see how it works was the precursor to then studying eventually in the 1950s electronics, passing electricity through in a guarded way so that you can make resistors, eventually the chips that you could have, and then computers, phones, all the materials that we have today. Housing, I mean, just to bring electricity into the house, we have to understand some of those same aspects, and that was that work that was going from candlelight and other things at night to eventually going to electricity, which was happening in the mid to late 1800s with guys like Alexander Graham Bell and Tesla. The competition between them was fierce. We're going to draw and say, how do we represent then, as they were studying this, force of electric push in a graphic way? Just like we had force graphically, which was a vector, you showed arrows in which way it pushed. We're going to use electric fields as an idea. And a field is nothing more than just saying, hey, if I put something here, what extraction or repulsion will it feel? Okay, it doesn't require two objects to know what that field is. It's usually one, and what is the field around it? It's action at a distance is what it was referred to. Now, to show graphically, when you put a single charge out someplace, what does that look like? It depends on, there's a couple of rules to drawing these electric fields. The first one is that the electric force lines always start and go out from positive charges. If you have a positive charge, there should be arrows going out, okay, from it. You can see those examples here. You don't need two. You could have just one charge like this object down here. The other one is that you're going to see the number of lines that are coming off from the object actually are going to show you what the field strength is. So if I move this up just a little bit so we can see some of these. Here's one that's more charged than the other. It's got more lines coming out of it, so it's more charged. Same thing with the negative. That one's more charged than this one. In all these cases, I don't even have one case where there's one object that's, I mean, the two objects have the same amount of charge. These are both the same charge. These are opposite charged. Here's an object that isn't even symmetrical. What's interesting about that is you're going to see the lines that come off of this pear-shaped sort of conductor is that when they come to a point like that, the lines get closer and closer together. When they come to a big, broad surface, the lines spread out. So it's weaker in electric field down here and a much stronger electric field up there. That's the reason that we put lightning rods in the tops of buildings so that if lightning strikes, it's actually going to find its way there first because it has the strongest field. Electrons are going to be motivated to move there and then go down by a wire instead of trying to travel through the wood and start the place on fire. Now, here's a third one. Electric lines should never cross. There shouldn't be two places that have the same value from two different objects. Okay, so they should never cross. Excess charge, like if you had, like I was saying here, well, these two have, you know, different charges, but they're the same values. So if this is one charge, that's two charges. At infinity, or, you know, 10 times the distance between those two objects, it's going to look like an object with the total amount of charge. So if this is two charges, one, if you get about 10 of these distances away, it's going to look like just a single object with three charges. Okay? If this is the case where this is like 4 negative charges and 2 positive charges, then the 4 negative charges, once you get 10 or so distances from the, or 10 or so of the distances between those two away, it's just going to look like 2 charges because the plus neutralizes out. And that's another reason that when we see atoms, which all have both positive and negative, but since the inside of the atom's got the positive protons and neutrons and the outside has the negative charges, by the time you get even 2 atom widths away, it looks like they're both covered, the pluses and the minuses, and so atoms don't set up electric fields because the pluses and minuses have no excess. Now, another thing that's interesting, if you put a conductor inside of a field, actually the first thing, if there were no conductor here, 2 flat plates will set up field lines straight between them. Okay, and since they're not spreading out, 2 flat plates like this will actually means that the strength of the electric attraction anywhere in that whole area between those 2 flat plates is the same. So not like when you get further and further away from a single charge, the power or the attraction of that electric attraction is dropping off. In 2 plates, if they're big enough and you're between those 2, the attraction is uniform between those, so they'll have a uniform attraction. Now, if you put a conductor in the middle, what will happen is it'll pull those lines of force in and go into the conductor. Now notice something is that if the lines are coming this way, that means the negative electrons are on this way, they're being attracted this way, the electrons are scarce over there, so it's plus. But you'll notice that nothing is in the middle. Any conductor will have all of its charge coming out you know, the lines of force, electric force are coming out from the outside, and nothing will be in the center. So if it was hollow, for instance, all the charge would be on the outside of the conductor and nothing on the inside. That's why it's safe inside of a plane if you're struck by lightning, or even in a car if you're struck by lightning. It's called a Faraday cage, where all the potential is going on the outside, but it will not come through. Even the thinnest of materials, if you can get so thin, you may have to be careful, like tin foil or something, but any width, hardly at all, would provide safety from other electricity. So those are different ways that we can show the amount of charge. These places where there's really concentrated lines is a strong electric field. These places where there's not many is a weak electric field. You're going to have a chance to draw several of these, so let's get some practice on that.